Okay. Okay, so I think we can get started. So today I want to talk about the negative cost cycle problem. So I think this week and in the past week, Dr. Costello introduced something about the single source shortest path problem, right? And I think okay. Single source shortest path problem. So let's just do a revision. So if there's no negative arc, what algorithm should you adopt? If there's no negative arc, then you need to use Dijkstra algorithm. And if you have a negative arc, but I think in the lecture slides, you are also told that there should be no negative cycle. Then what algorithm should you use? Can you still use that Dijkstra algorithm? No, right? So if there's no negative cycle, you should use Bellman Ford. Okay, so then the very natural question is why you cannot use Dijkstra algorithm when there's no negative, when there is negative arc. That's to say, you can use Dijkstra algorithm if and only if all the arcs are positive in this graph. So you remember how to prove it? Okay, so let's look at this example. So suppose this is your source, and so first, do you still remember how does the Dijkstra algorithm functions? That's to say how it works. So the Dijkstra algorithm works in this way. It gradually grows a tree, a spanning tree, from your source S. And the problem that you want to solve is that, so suppose this is your source, and you want to know what is the length of the shortest path from S to any other vertices in this graph. So it is a greedy algorithm. Every time, so initially, the distance from S to S itself is 0. And you initialize the distance for any other vertices to be positive infinity. And then you select the shortest distance. So suppose from S you can go to some vertex A. And then in the next step, what do? For all those arcs that are adjacent to A, that's to say, you can go from A to other vertices. You update their distance, right? You update their distance. Let's say from A, you can go to B, or C, or D. So before this step, before you connect S to A, the distance from S to B to C and to D, they are all positive infinity. And because now you have connected from S to A, so there's a possibility for the shortest path to be from S to A and then from A to B, or from S to A and then from A to C, right? So in this way, you should update the distance to B, C, and D. And then, okay, so these are the nodes that you have already explored. Next, what do? So among all the nodes that are not explored, so now we have explored S and A. So among all the nodes that are not explored, you select the one with the shortest distance from S to it. Let's say now to B, it is the shortest distance. So we include B into your into the sets that you have already explored. And then you update all the nodes that are adjacent to B. You update their distance, so on and so forth. So it is possible that if you go from S to A and then to C, This is a distance, say, d1. If you go from S to A to B, and probably say you can go from B to C, it is possible that SABC is a shorter distance. And be careful that in reality, the distance of AC is not necessarily longer than A to B and then B to C. This does not possess the triangle inequality. So because C is not included in the set that is explored, so it is possible that you find that, you can go from B to C, and you find that if you go through SABC, this is a shorter distance than SAC. So you also need to update the distance label for C. Okay, please take a seat. So this is the general idea of the Dijkstra algorithm. So why is Dijkstra algorithm correct? So suppose this is your S, and you go through some tree path U. And let me change the color. So suppose this is the closure of a set that you have already discovered, or say already explored by the Dijkstra algorithm. All those in the red circle. So then suppose suppose in the next step, so as I said, all the nodes in this red circle are already explored. So suppose in the next step, you find that, okay, so U to V, this is the shortest, V has the shortest distance via going through U. That's to say you go to S to U and then to V. Suppose this is the shortest. And let's say UV has less 10. Then for any other SV paths, okay, so let me write. Any other SV path must go through some node B, not in the explore set. Or say, what does this mean? This statement says that, so there must be some B outside of this red circle. For any other SB path, you must go through, say, go to some vertex A that is still in this set, and then U to B outside of this red circle. And there might be some paths from B to B, right? Why? Can you tell me why? So let me repeat. The path, the arc from U to V is selected by Dijkstra algorithm. That means this is the shortest. Or say, because in every iteration of Dijkstra, you need to choose the node that is outside of the red circle, such that it has the shortest distance. So suppose in the next iteration, you choose V, and you connect U to V. Then I say that for any other SV path, you must go through some node B that is not in this red circle. Why? Thomas, can you tell us why? So think about, how does Dijkstra work? Dijkstra works in a way that every time it selects the one with the shortest distance, right? So that's to say, if you do not need to go through this B, you can go through other vertices. Say you go through some C and directly to V. Then this from C to V should be the shortest, not U to V, right? This is how Dijkstra works. Every time you select the shortest. So that's to say you must go through some node that is outside of this red circle. Okay, so let me note here. So this red circle means that nodes that are explored Dijkstra. All right, so first we need to clarify this. And then what else? Then we can say that from S to B, the distance from S to B must be greater than or equal to the distance from S to B. Why? First, I say that for any other SV path must go through some node B that is not in the Explorer set. And then I can conclude that the distance from S to B must be greater than or equal to S to B. Why? This is still because Dijkstra algorithm is a greedy algorithm. So you need to choose, in every iteration, you need to choose the shortest. So if S to B is less than S to B, then in the next step, you should not choose B, you should choose B, right? Not B. Okay. Oh, by the way, for those who can later, here I'm explaining why Dijkstra only solves positive arc cases. So because I think you have already learned in class that when you are using Dijkstra algorithm, you cannot apply to any graph with negative arc. This is what I'm explaining now. So now we know that S to B must be greater than S to B. However, if B to V has negative cost, then what happens? Suppose B to V has negative cost, then it is possible that you go through S to A, then to B, and then through this negative cost path from B to V. Along this can be shorter than S to U to V. Then Dijkstra is wrong, right? So here I'm explaining. Okay, so if B to V has negative cost, then it is possible for S to B and then to B. This is less than S to B. So this explains why Dijkstra algorithm cannot deal with the negative cost cycle problem. Okay, so this is just I tell you this just to help you to review what you have learned in class about the Dijkstra algorithm. Next, we look at, suppose a graph has negative arc, but there's no negative cycle. Then how can we use Bellman Ford algorithm? And I remember I explained in the previous section that when we are talking about the single source shortest path problem, we assume that there's no negative cycle. Otherwise, you can just iterate in this negative cycle to as many times as you can, and your and the path is not bounded from below. So when you are transforming this into a linear programming problem, it tells you that the optimal solution just goes to negative infinity, right? So when we are talking about the shortest path problem, we assume that there's no negative cycle. So now that Dijkstra algorithm cannot be used to deal with the case in which there is a negative cost arc in a graph, so we need to turn to Bellman Ford when we have negative arc. So what does Bellman Ford do? Can anybody just tell me? So first, I need to clarify. Have you learned this in class?
Yes.
Okay, so I have learned this in class. Can anybody tell me what does Bellman Ford? How does Bellman Ford do? What is the ideology?
It's like, I know it uses the while loop.
Yes, while loop.
A while loop and an inequality. And so basically it makes it so that like it goes back and checks.
Yes, you are right. So Thomas tells us that to use a while loop. So in your lecture slides, I just write roughly. Okay, so you have a list. Initially, you put your source node into the list, and you create a while list is not empty. Is that what you're saying, Thomas? While the list is not empty, then you remove, say, element I from list. This element I can be, say, the first element or the last element, whatever. So then for each ij in the arc set, if dist j is greater than dist I plus cij, then you update dist j. This is equal to dist I plus cij. And if j is not in list, add j to list. This is what was written in the lecture slides. You don't need to copy because you can just copy and paste from the lecture slides. And actually, when I learned Bellman Ford, I didn't learn the way to use the while loop, but it is like this. So we let distance of s equals to 0. S to itself must be 0, and dist x equals to infinity for other nodes x. So this is your initialization. But of course, in this case, you also need to initialize dist s equals to 0, dist of other nodes to be infinity. And then I use the for loop. Say for I from 1 to v minus 1. And for each u, v in E. That's to say we have a nested for loop. In the first for loop, we say that, okay, so for this iterator, we iterate from 1 to v minus 1. This is the node set. So that's to say, suppose we have n nodes, then the first for loop iterates n minus 1 times. And then for each arc uv in E, what do? I just say dist v equals to minimum of dist v and dist u plus, say, cuv means the cost from u to v. Okay. So my next question is, why this also works? Because in this case, if you are using a while loop, seems that whenever you are using a while loop in programming, you do not know how many times it should iterate. But when you are using a for loop, you know how many times it should iterate. But in this case, I set that for this loop, I set for I equals to 1 to v minus 1. Why am I sure that I can solve the single source shortest path problem at most in n-1 iterations? Why am I sure? That's to say, in this case, it iterates at most n-1 times. So my question is, why Bellman Ford is true? So to answer this question, you first need to know, what does Bellman Ford do? What does it do? look at the pseudocode there. Let's just say we iterate for n-1 times, or say v-1 times. And in each time, we just check every arc in the arc set. And we try to update the distance by this dist v equals to, for each uv in E, dist v equals to minimum of dist v or dist u plus cuv. That's to say, if you can go from the source via some path to u, and then from u to v. If this distance is shorter than your previous distance, that let's say you go through another path to v. If from S to U and then U to V is shorter, then you update. So why does this make sense? So essentially, I want to say that for every node V, the shortest path from S to V has at most V minus 1 arcs. Look at this statement. For every node V, the shortest path from S to V has at most V minus 1 arcs. That's what does this tell us? S is V. So the worst case scenario is that you traverse every other node to V. This is every other node. And this is the worst case scenario. In the worst case scenario, you traverse every other node, and then you find that, oh, this is the shortest path from S to V. So for I from 1 to V minus 1, every time you are just trying to update. So how can we interpret this? So look at the for loop that I have written there. When I equals to 1, what can you say? You can say that for those nodes such that in their shortest path from S to itself, if the path has length 1, then when I equals to 1, they are done, right? As you say, suppose from S to U, you go from S to U, this is already the shortest path. Then when I equals to 1, this guy is done. Then when I is 2, then when I increases from 1 to 2, suppose for some node X, the shortest path is S go to some node and then to X. This is the shortest. Then when I equals to 2, X is also done. So on and so forth. In the worst case scenario, from S to a node V, you should traverse every other node. And this path has length V minus 1. So that's to say, in the worst case scenario, you do the outer for loop for V minus 1 times, then V should also be done. So this explains why Bellman Ford makes sense. And also I can say that this can be shown by induction. And what I have told you is just the induction, because in the base case, suppose S to U, the shortest path has length just contains 1 arc, then you are done. And suppose, say, from S to some node Y, this has length I minus 1, and from Y to V. And then you can construct an induction by this, right? In the first I minus 1 iterations, this guy is done. Then in the next iteration, this guy is also done. Okay. So this is about Bellman Ford. So now that we have reviewed Bellman Ford, the problem of negative cost cycle can be solved. Can anybody tell me how? I give you a hint. Use Bellman Ford. How can we detect a negative cycle? Another hint. If there's a negative cycle, say from S to V. So suppose this is the negative cycle. Then you can go through this negative cycle for as many times as you want. two hints. You use Bellman Ford, and suppose there's a negative cycle. You can just go through this cycle as many times as you can. So how can we use Bellman Ford to detect the negative cycle? Thomas, we trust you. Can you have a try?
I just to detect whether one exists.
Yes. So I just want you to check whether there is a negative cycle in this graph. Not necessarily telling me what the hell, where it is.
Yes. Yeah.
Mm-hmm.
Wouldn't that mean that we could just keep decreasing? So wouldn't it never would it happen?
Right?
So like if Bellman Ford never completes.
Yeah. So roughly correct. So that's to say, if there's a negative cycle, then this while loop never ends. Never ends if there exists negative cycle. This while loop will never end. Because in this way, for the shortest path from S to B, it is like you should go through this negative cycle as many times as you want, and then you to B. So the shortest path should have positive infinity arcs, not just the V minus 1 arcs. So if you want to detect a negative cycle, you just need to make a small modification to Bellman Ford. Say at here you select something like you create something like a timer equals to 0, and on this while loop, in every iteration of this while loop, you just set say timer plus timer equals to timer plus 1, and you set an if statement. If timer is greater than or is greater than V minus 1, then you can conclude that there is a negative cycle. It's because this while loop will never end. And as I said here, the while loop should iterate at most V minus 1 times. So you check the timer in every iteration of this while loop, then you are done. So this is about the negative cost problem, the negative cost cycle problem. This is all for this week's section, because yesterday I checked with Dr. Costello about the contents, but because we have 20 minutes we still have 20 minutes left. So I think I can also tell you something about efficient implementation of the Dijkstra algorithm. So implement Dijkstra. Okay. So think about this, as we have already reviewed Dijkstra algorithm. You have two sets. Set 1. You have two sets, set 1 and set 2. And set 1 and set 2 are disjoint. And if you add them up, they just construct the set of all the nodes. Set 1 means nodes explored by the algorithm. And set 2 means that nodes not yet explored. Here I say explore means that you have already added this node into the tree. So Dijkstra algorithm, essentially, finally you should get a tree, right? You should finally get a tree if you use Dijkstra algorithm. And later on in this course, you should learn something about minimum spanning tree. And in minimum spanning tree, you will. So what is the minimum spanning tree? So I give you a graph. So what is the tree? A graph with in which every arc has weight. So what is the tree such that the nodes of the tree is just the nodes of the graph, and it is a tree, and it should have minimum weight. This is the minimum spanning tree problem. And in minimum spanning tree problem, you should learn some algorithm called Prim's algorithm, which is also a greedy algorithm. So Prim's algorithm, which you should learn later, is very similar to Dijkstra algorithm in its process. So in Dijkstra algorithm, finally, you should be able to obtain some tree. So if you don't know why Dijkstra algorithm returns a tree, review your notes or review the lecture slides. And so you have set 1, which is the set of nodes that have been explored, and set 2 is the nodes that not yet explored. And in every iteration, in each iteration, what do you need to do? You need to select the node from set 2 with the smallest distance to S, right? So in each iteration, you need to select the node from set 2 with the smallest distance to S. And then update the distance of nodes that are adjacent to, let's say you select node I. Then you update the distance of nodes adjacent to I. And of course, these nodes should be in set 2, not set 1. Because set 1 are the nodes that you have already explored by the algorithm. Or in other words, the nodes in set 1 have already been included in this tree, which is finally returned by the Dijkstra algorithm. So how can we optimize this process? So you have a set 1 and set 2. Say in set 1, you have N1 nodes. In set 2, you have N2 nodes. And N1 plus N2 equals the number of nodes, right? Set 1, set 2 is a partition of the node set. And we say that in each iteration, we need to select a node from set 2 with the smallest distance to S. Then if you want to select the node with the minimum distance, what should you do? You need to traverse the set 2, right? You need to check, okay, is this one a minimum? No. Is this one a minimum? So on and so forth. You check the whole set. And it costs you N2 iterations to check. And then you need to update the distance of the nodes adjacent to this I. So if you just use, say, 2 lists, if you are a Python user, you just use 2 lists to be this set 1 and set 2, and every time you just traverse the set 2, and you check which one is the smallest. This the overall time complexity should be OV squared. Why? So how many iterations does a Dijkstra algorithm should run? It should run V iterations, because in each iteration you add 1 node. You remove 1 node from set 2 and add it to set 1, and there should be N nodes from set 2 that you should add to set 1. So you should run N iterations, and in each iteration, you need to traverse the set 2. So this is OV squared, right? However, if you have studied data structure and algorithm, there is a data structure which is efficient called min heap. So what is a heap data structure? Thomas, have you used to data? Okay, then this will not be tested in your exam, just for your interest. Okay. So what is a heap structure? So heap, it is like a tree. It is like a tree structure. It is a tree structure. But it is a tree structure, but every node just has 2 descendants, like in this way. Right? So suppose you have n elements. Because 1, 2, 1, 2, 3, 4. So the heap has height log n, right? And what does a heap tell us? So a mean heap means that for every node, it is smaller than its two descendants. Let's say this is node A, and this is node B and node C, and D, E, F, G. So in a mean heap, what we have is that A is less than B, and A is less than C. But for the relationship of B and C, not important. Let's just say B can be greater than C, or C can be greater than B, whatever. But I just need to make sure that A is less than B, and A is less than C. And also, because B has descendants D and E, so we should have B is less than D, B is less than E. And C has descendants F and G, so C is less than F, C is less than G. Why is heap useful? So first, I have told you that heap has height log n. So every time you want to, so what can we do is that we should put the set 2. We should put this guy into a mean heap. Suppose we do this. Then, because every time we want to select the node from set 2 with the shortest distance. So who has the shortest distance? This guy, right? Just the root of this heap. Because A is less than B and A is less than C. And B is less than D, B is less than E. C is less than F, C is less than G. So A should be the minimum, right? A should be, this guy should be the minimum. So every time when we want to select a node from this heap, we just select the top one. However, we need to maintain this heap. So what do we maintain this heap? We just choose the smaller one between B and C and move it upwards, and so on and so forth in an iterative manner. Because I've already moved the C here, so I need to determine F and G, who to replace, who to take this place, so on and so forth in this iterative manner. This, but don't worry, this will not be tested in the exam. So if you are interested, you can look up some resources online about heap. So that's to say, when you are using heap, if you don't use heap, then in this step, you select node from set 2 with the smallest distance to S. This costs order V time. This costs order V time. But if you're using a heap, it costs order log V time. Because a heap has height log n. Right, so this is an efficient implementation for Dijkstra algorithm. But this is just for your interest. So I think I have already finished the content this week. We don't have that much content this week. Make sure that you understand how does Dijkstra algorithm work? How does Bellman Ford work? Why do they make sense? This is more important. Why do they make sense? Because I think you might encounter some proof problems in your either homework or in your exam. So make sure you understand why do they make sense and how to use Bellman Ford to detect negative cost cycle. So that's the end of this week. So I think we can end earlier. Okay, thank you.